Okay, so as we start with the extra session, this is more like a revision. And so, as the title says, it's about electromagnetic theory, and all throughout the course, we started from electrostatics to magnetostatics, and then we gradually moved towards electromotive force and how changing electric fields can result in magnetic fields and vice versa. And from there, we saw the final forms of Maxwell's equations. And then we moved towards electromagnetic waves. We discussed about reflection and transmission of waves as they propagate through different media. And in the last part of the course was about transmission lines, antennas, and waveguides. Right. So today's class will be this revision kind of thing, which where I'll just talk about and brief about or summarize what we had discussed all throughout the course. Okay, feel free to have share any comment or anything if you want to ask. Okay, so when we started, we saw that in general, like if you talk about the major forces that are there in universe, there is the strong forces, electromagnetic forces, weak forces, and gravitational forces. And out of this, we saw that strong forces or weak forces, they are very short range forces. So when we talk about the kind of effects which are very dominant in our day-to-day lives, these forces do not play much of a role because strong forces mostly deal with, you know, protons and neutrons, and weak forces are associated with radioactive effects or phenomena. And then what's left is the gravitational force and the electromagnetic force. And out of this, what is seen is that gravitational force is also long range, and it also has the 1 by r squared dependence as electromagnetic forces. But the difference is that the gravitational forces are dominant in cases where we have large mass. Okay, while in when we talk about celestial bodies in those conditions or under those mass inertial ranges, gravitational forces are very significant. But if you talk about our regular lives, there it's the electromagnetic force which is more more pertinent. So there comes electromagnetic forces. And when we talk about electromagnetic radiation, it's basically if you have any charge which is in a accelerated motion, we saw that it has a radiation associated with it. So it there is a transmission of energy from that charge as it accelerates, and that energy is carried in the form of some radiation, which is the electromagnetic radiation. Right. So the course started with electrostatics, where you have charges fixed in certain distribution. So either you can have static charges, or you can have static discrete charges, or you can have a charge distribution, continuous distribution. And based on that, you can say that if you have such a distribution, and now if you bring another charged body near it, what would be the force it would experience? And that is what is given by the Coulomb's law. So here we know that if you now have a continuous distribution, you have to modify the Coulomb's law by the integral, where the integral happens over the distributed charge distributed region. Okay. So in case of line charge, you have this lambda dl. In case of surface charge, you have sigma dA. Okay. And in case of volume charge, this is how it looks like. So rho is the rho, sigma, and lambda are the line charge density, surface charge density, or volume charge density, right? So this was at like this started quite at the this lies at the very early stage of electromagnetism, where initially electric field and magnetic field was considered separately, right? So this is about electrostatics, where you talk about charges. And we started with electrostatics. That means things are not changing with time, they are fixed at a position, and we see the effects, we see the force that one charge experiences because of the other. So that is given by the Coulomb's law. Now, interestingly, what we saw is that the flux of the electric field. So because you have a field, so there will be field lines. So if you have some object, there'll be field lines entering the object and leaving the object. So you can define a quantity called flux. Okay. And if you have a defined surface, you can find the flux as E dot dA. So surface integral of electric field over that surface will give you the flux. And what what was seen is that there's this interesting thing about electric field where if you have some, some charges outside, so you have some closed object and then you have some charges outside, so the flux lines will enter the object and also leave the object. So in a way, this would not have any effect on the net field that that is there inside the object. So what matters, what was found is that if you have some charge enclosed in a region. So if you have a region and if inside that there is a net charge, it is that charge inside which plays a role in defining the field that is there in that region. Okay, so that means if you have some closed quantity like this, if you have charge outside, that does not define the field that you have here. But if you have some charge inside here, okay, so if you consider a closed region here, okay, enclose a closed region enclosing a surface, and if there is or closed surface enclosing a volume, and if you have some charge enclosed within it, then the electric field, you can say that the net flux coming out of that surface is given as E dot dA surface integral, which is equal to Q enclosed by epsilon naught. So the total charge enclosed is what matters. And why it was interesting is that this enabled us to, first of all, this led to the first Maxwell's relations, but this also helped us in solving for electric fields and magnetic electric fields in a much easier fashion, or also the potential calculations. All those things became much simpler, especially when symmetry was involved, right? So we did a lot of questions based on how one can use Gauss's law to find electric fields without doing much of an integration, right? So this Gauss's law finally, so if you look at this, this is a integral form, and you can also write it in the in differential form by using the relation, by using this relation. So this relates surface integral to the volume integral, right? So from here, what you can do is you can write Q enclosed as rho d tau, and you can use this divergence theorem to relate the surface and the volume integrals. So you can rewrite the Gauss's law in terms of this differential form, and this is what gives you the divergence of electric fields. And if you remember, when you talk about vector fields, in order to define any vector field, you need divergence and you need curl, right? So this sets the divergence of the electric field for a given charge distribution, okay, in a given media. In free space, it is epsilon naught. In some other media, the permittivity of that medium will play a role, right? And then we could see that you can do direct integrations, or you can use Gauss's law by using this kind of equations to finally find the charge density. Suppose you know the charge density, you want to find the electric field. So all this kind of uh, questions we had solved where we used this relation, right? So this was about Gauss's law. So that was the divergence of curl, and then came the curl of E. So what we saw is that if you do a line integral of electric field over a region, and if it is a closed region, okay, so if it is a closed line integral over some path, it was seen that in case of electrostatics where things are not changing with time, there this turned out to be zero, right? And from there we could see that that means now you can use the Stokes theorem, which relates the line integral to surface integral. Okay, so this closed line encloses a surface, right? So you can relate the surface integral and the line integral by this relation. So this tells us that the curl of E goes to zero in the electrostatic limit. And from there, we could finally define a term called the scalar potential, which is given as E equal to minus grad V. Okay. And this is what is valid for the electrostatic case. Later, we had seen how things evolve under the situation where we have time varying effects, right? So now, this also simplified a lot of our ways of finding electric fields because, it's a scalar potential. So dealing with scalars are much easier. So in many cases, we first find the potential and then use this relation to find the electric field. And now if you include this relation and try to write the Poisson's equation in terms of the potential, this is how it looks like. And this is called the Poisson's equation. And if you have no charge density, in that case, what you get is the Laplace equation given as del square V equal to 0. So any solution of Laplace equations are called harmonic functions, and we had seen how different ways of solving for such Laplace equation questions, right? And basically, this was the summary which told us how, if you know rho, you can find electric field or potential and vice versa. So all these relations. Now, after that, we moved to a particular case which is about conductors, right? And there, what we saw is that in general, so if you have some electric field, if you have a charge there that is known to experience some force. So now if you have a conductor which has a lot of free charges, they these free charges inside the conductor will also experience certain force in the presence of an applied electric field. So the interesting thing about conductors was seen is that the charges redistribute in such a way that the net field inside the conductor is cancelled, right? So the net field goes to zero. Okay. And that means the charges get distributed in such a way that all the charges lie or get arranged on the surface of the conductor. Rho inside, or the volume charge density, goes to zero. Okay, so all net charges reside on the surface. And from there, because the electric field is zero, that means you can say that the surface of the conductor is an equipotential surface. So no work is done in moving a charge from this point to this point. Okay, so all the electric fields are perpendicular to the surface, not along the surface of the conductor. Later, when we spoke about dielectrics, we saw that they will also have a similar effect, but because it's a dielectric, there this induced field in the opposite direction will not be equal to the applied field. So you will have a resulting field inside a dielectric medium, while for a conductor, this would go to zero, right? And then we saw that one can use this concept to actually, shield the effects of the external effects of, so if you have some charge here, and if you say that I don't want this region to be affected by any charge that I bring here. So what you can do is you can shield this region by a conducting surface, right? So this is what was one of the questions, and we solved it and we understood that if you have some charge here, some charge Q here, so this would result in a non-zero field here. But the field inside the bulk of the conductor will go to zero. Okay. And if you bring some charge Q outside the conductor, that would affect the field outside the conductor, but that would have no effect in this cavity that is there inside this conductor. Okay. So this was one of the typical questions that we solved. And here it was seen that on bringing any third charge here, your sigma A, sigma B did not change. Only the field outside or the sigma R on the external surface changed, right? So sigma A and sigma B or the fields in this region are not affected by any changes that you do in this region. Neither if you add any charge here will the field in this region be affected. So this is completely isolated, right? So this is one of the way of shielding uh, a region from external field effects. And we saw that from our from the relations of divergence and curl, we could define certain boundary conditions. So if you have a charge distribution, okay, some surface charge on a surface, and we know that this is how this comes from the Gauss's law. So you from here, what you can now say is that if there is a net surface charge on this sheet, then the electric field, the perpendicular component of electric field above and below should follow this relation, while the longitudinal component or the parallel component will be continuous. And using this relation, you can try to define the surface charge in terms of, so if you know the potential, suppose, and you know that it's the discontinuity is only in the perpendicular direction, so you can write that if you know the potential, you can use this relation to actually find the surface charge density. So we did solve certain questions when we talked about Laplace equation where this relation was used. Now talking about polarization, so this is what is the fact. So if you now have some medium, because there'll be some charges, some free charges inside, and they'll rearrange in such a way in the presence of an applied field that there'll be a net field, right? That is what happened for the conductor as well. So now consider a dielectric medium where similar things will happen. So you do have some rearrangement of the charges that are there inside. So that actually what it does is it results in a net field inside, and which is a polarized field. So that happens because the charges get polarized. Charge distribution gets modified in presence of the applied field. Okay. So now if you say that the net dipole moment, so what happens is you this polarization can be quantified in terms of the polarization which is given as dipole moment per unit volume. Okay. So how do you define it? So if you have some atom in presence of some electric field, you would know that the electron cloud will distribute in such a way that it would shift in this direction based on the electric field applied, right? So that means you would have a more of a minus charge here, more of a plus charge here. So in a way, that results in a net dipole moment. Okay. So now if you know the dipole moment per unit volume, which we term it as polarization, this polarized electric field will also have a net effect, right? So you have to consider that in cases in mediums where there can be a finite polarization. So there, this polarization can result in a net potential. And how do you define it? So you say that if you have a dipole at some distance r, then the potential is given by this relation here. So now if you have a region where the dipole moment per unit volume is given, then you can write the potential as this volume integral, right? So P here is the polarization. And then we did all this, use the, relations. So in order to simplify or write it in a more, uh, so we do some rearrangement basically. And once we are doing that, why we are doing that is, so this will give you finally this form of the potential, which is telling us something. And it hinted at the fact that now the potential, because of this polarized object, can be written as effect of two terms. The first term involves a surface integral. So here P dot n cap will be the surface charge. Okay. And then you have a volume integral where you can now say that the divergence of P minus of divergence of P will be your volume charge. So that means the field due to any polarized object for a given polarization P can be written in terms of two potentials, one for a surface charge given as P dot n cap and another for a volume charge given as minus divergence of P. Okay. So these are bound charges. These are not free charges that you apply. Rather, this happens by itself in the object in presence of some applied field. So these are bound charges, but they also result in an effective field. So now that means, if you have to write the Gauss's law in for a medium where there is a net polarization, you have to consider the volume charge density for both of the cases. So there'll be a free charge which you apply, but there'll also be a bound charge that is resulted inside the media. And so if you now modify the Gauss's law, you would have this term. So here in place of PB, you write it as minus divergence of P, rearrange the terms, and there you get this expression. So D here is the electron displacement, which is defined as epsilon naught E plus P. Okay, so here you have to understand that E is the effect of all the electric field. This electric field is arising because of all the charges, not just the free charge. It's for the free charge as well as for the bound charges. Okay. And D here, this term here is actually dependent only on the free charge that you apply. Okay. And so you can just now this P, the polarization will again be a function of the medium that we were talking about, right? So the medium, it's a medium property which determines how much of the polarization will happen for a given field. So if you consider this, proportional relation with electric field, you can rewrite it further where the medium properties come in as this permittivity term here, right? So if D is the electric displacement, which is only affected by the free charges, and epsilon is your permittivity of the material, E is the net electric field because of both the bound and the free charges, then they are related by this relation. Okay. And this epsilon here, so now if you write it, normalize it with epsilon naught. So epsilon by epsilon naught is what we call the dielectric constant of our medium. So this is how the Gauss's laws get modified in presence of a polarized medium. So then what we try to do is we try to solve for the Laplace equation. So why? Because we saw that if you have a scalar potential, so if you can find the scalar potential first, you can use the scalar potential to find electric fields or charge distributions and all of that, right? So that means now if you have a region, you can first try to find the potential. Now consider first a region where there is no net volume charge density. So it follows the Laplace equation. And from there, we try to solve for V. Interesting things about the solutions of the Laplace equation is that Laplace equation is a kind of averaging instruction. So any point is basically the sum of the neighboring points. So if it is in a line, then x Vx will be a summation average of x plus a and x minus a potentials at the two neighboring sites. If you have a volume integral, like if you have some in 2D, it would be something like this, or in 3D, it would be something like this. So it's basically average potential, average of a neighboring region. Okay. And Laplace equation tolerates no local maxima and minima. And this is a very important point because this finally led to the uniqueness theorem, if you remember. So how did we decide to solve the Laplace equation was that this is how a Laplace equations looks like in 2D, right? So what we do is we look at the questions or the conditions given. We set the boundary conditions. What is the potential at the different boundaries? Okay. Once we have the boundary conditions, we try to write. So because it's in 2D, what do? We say that the potential has this kind of is written in terms of a product of some function of x into some function of y. And then we do this separation of variables to finally get two separate equations. So the first, so as you can see, and there is some constant. So we take the constant to be k square. Why? Because that simplifies our mathematical calculation. Okay. And now we solve this individual equations. Okay, so this is a way of solving differential equation by separation of variables, and that's what we do. And there, based on this boundary conditions, we choose our constants, whether positive or negative, and we get an expression like this. Once we get an expression like this, we keep on applying the boundary conditions, the other boundary conditions, to finally find an expression for the potential. There in that process, what we do is once we find the general form of the potential, we say that because it follows superposition principle, we can write it as a sum of all possible solutions. Okay. And then the final condition is that, so when you have a non-zero some potential, okay, so one of the conditions you have to use at the last stage where you use the Fourier trick. So that makes use of the orthogonality of your function. Okay. So if you have a sinusoidal function, you will use the orthogonality relation of sinusoids. Later, when we spoke about spherical coordinates, we used the orthogonality conditions of Legendre polynomials. So based on the polynomials that we have or the functional form that we have, you have to choose the Fourier trick. And using that, you get the expression of your coefficients and finally the expression of your potential. So once you find this expression, now you can use this potential, like use the expression of the potential to find surface charge densities um, or electric fields and all of that. Okay. So this was one of the questions where you had the, so the potential was given, found out, like based on this expression, what we did. But now what would be the surface charge density? And there we used this relation, which again came from the boundary conditions, if you remember. Okay. So using a derivative of doing a derivative of the potential, you could actually find an expression for the surface charge density. Right? And in case of spherical coordinates, the main process is the same, but there now you have to write your potential in the spherical coordinates. So it will involve r, theta, and phi. If you consider azimuthal symmetry, this term will go away. So there you consider v to be a function of r and theta, product of functions of r and theta, and do the separation of variables. So here, this expression that you get for the angular part, this the solutions to this are the Legendre polynomials. And there again, when you solve for the potential, you have to use the orthogonality relation of Legendre polynomials. In case of the radial part, you have an expression like this. So there we saw that based on what your possible values of r can be, you have to choose the functional form of the radial part. What I mean is that if you have a question like this, where you have a hollow sphere, so if you are asked to find your potential at the surface is specified, you have to find the potential inside. So there you have to consider the linear, the radial part as just AL r to the power Ly, because 1 by B, sorry, B by R is there, right? Where is that? So B by R to the power L plus 1. So here, if it is inside the sphere, your one possible value of R is 0, and that then this term will blow up. So you cannot have this term. So when you talk about inside the sphere, there you take this form of the radial component or radial part. But then if you are asked to find outside the sphere, so there again you have to take this form. So that if you use this form at very large distance from the sphere, this term will again blow up, right? So there you have to use this form. So based on which region you're talking about, what are the possible values of R, you have to choose the, the functional form of your radial part. And then you have to, so if this is the form, then you apply the uh, orthogonality condition to find the expression for your coefficients, okay, which is similar to how we did for the rectangular coordinate systems as well. So basically, you use the Laplace equation, solve for the potential, use it to find electric fields, and then use this boundary condition to actually find the surface charge density. So this was one of the, so some of one class I think was dedicated to understanding this solution of Laplace equation and how one can use it. So interesting thing about the solutions to Laplace equation was that it cannot have any, it does not support any local maxima or minima. And from there, we got this uniqueness theorem, which said that if your potential is specified on the surface, that is enclosing some volume, then if that value is specified, then the solution to Laplace equation inside the volume, that means the potential inside, that is uniquely determined. Okay. And this uniqueness theorem again led to our method of images. So this led us to the fact that if you have some charge distribution and if you're asked to find the electric field or the potential for some given charge distribution, you can always use a simplified version of this charge distribution such that the boundary conditions remain the same. So if you have a condition where you have some sheet, conducting sheet where the potential is 0 and you have some charge q here, if you're asked to find the potential in a region above it, so you can remodel this same distribution by saying that now you don't have the sheet, but you have a minus q charge such that the potential again on the xy plane goes to 0. So basically, if the boundary conditions remain the same, that means the potential that is defined on the surface enclosing the region, that is the same. So that means the potential that you would get in the region here, the region of interest for this case is the region above the plane. So the potential that you will get for this case and this case would be the same. So that comes from the uniqueness theorem. So this was one of the relations where, so that means whatever is given, if you can remodel it with some simpler, um, simple, discrete charge systems maybe, that would also give you the same potential. And from here you can also find the force. Okay, you can find the surface charge density and all of that. Important to know that the work done will be different, because here you are bringing two charges, while here you are just bringing one charge. Okay, so similarly, this is a very, very, common question, but a very fundamental one. So this is like a, we did solve this. So if you have a grounded conducting sphere, so the V on the surface is 0, you have some charge Q here, find the potential somewhere outside. So we saw that you can have the same distribution. So you can have V equal to 0 if you again put a Q prime charge inside, okay, where Q prime is given by this and B is the distance from the center, which is given by this relation. So if you have this kind of a distribution, the net field that you would have in this surface would still be 0. Okay. And then this is just a discrete charge system distribution, so you can use it to find potential or force. Okay. And there were many such questions that we had solved for using the image charge concept. So this was about electrostatics. And there we saw that the electrostatics talks about constant electric fields, right? And then we moved to magnetostatics, where we talk about steady currents. So that means if you have a loop of, some wire where through which some constant current is flowing, that would result in some field. And that would be given by this relation here, which is called the Biot-Savart's law. Okay. And we saw that, using this, we tried to find the field for an infinite wire, and it had a form like this. And now what we tried to do next was, because now B is again a vector field, right? So we have to find ways of defining the divergence and curl of B. Because if you can define divergence and curl, then you can actually define B, right? So before that, what we try to see is that what happens to the forces. So we know the Coulomb's law. We know that if you have a charge Q in some electric field, we know that the force is given as Q into E. But now if you have a magnetic field, what would be the force that it would experience? And there what we saw is that we have this expression which comes from the Lorentz force. And so the magnetic force is given as Q into V cross V, which means that this force is directed in a direction perpendicular to B and V, which results in the fact that magnetic forces do no work. It does not. So there's no work done by the magnetic force. Okay. So if you have some current carrying, some current carrying wire. Okay. So there you can try to write the magnetic force that one can feel in the presence of this current carrying wire. And this would be given by this expression here, which again comes from this Lorentz force relation, right? And this was what was again used when we spoke about electromotive force, right? And these are, now if you have a surface current, which is, so the surface current density is defined as K, then you would have the magnetic force defined by this relation. And if you have a volume current, then this is how it looks like. So these are very, straightforward things. But then what we wanted to do finally is that we know the divergence and curl for electrostatics. We also wanted to find the divergence and curl for magnetostatics, right? And because there is, so uh, magnetic monopoles do not exist, which resulted in the fact that divergence of B is always 0. And the curl of B is given by mu naught J. So this relation, the Ampere's law, will can also be found from, you know, this relation that, sorry, from this relation that you have here, from the Biot-Savart's law. So just as, like, it's similar to, it's analogous to the Gauss's law that you have for electric fields. Okay. Now, here what we saw is that one easy way of finding electric field was potential. Similarly, what we saw is one easier way of finding the magnetic field is to define a vector potential, and we define it as this. So we define some term A where B is given as curl of A. Okay. And so now if you rewrite, you would get an expression like this, right? So as we had very recently also discussed, the absolute value of potentials do not make any it's not very important, right? What is important or what is physically useful to us is the electric field, magnetic field, intensities, these values. So what is the absolute value of B does not matter. We can always add some constant to it. So similarly, if you have some vector potential, you can always have some extra terms to it such that the magnetic field do not change. So because of that, what we saw is that you have the freedom to choose a such that divergence of A goes to zero. Okay. And if you do that with that simplification, you would get a simpler version of your, this Ampere's law in terms of a vector potential now. So now that if you know the volume current density, you can try to find the amperes, you can try to find the vector potential and then use this relation to find magnetic field. So we did solve questions where we first try to find A and then use it to find B. Okay. Now, just like we had boundary conditions for magnetic fields, we also had, for electric fields, this is given by this relations we just discussed. So similarly, this relation, so if you have divergence of B going to zero, which comes from the fact that there are no magnetic monopoles, so this results in the fact that, so if you have a surface, because the divergence is zero, that means the normal components are always continuous. Okay. While now if you use the curl of B, the curl of B involves this volume charge density, right? A volume current density. So that means now if you have a net current flowing through a volume, or in case of 2D, if there is a volume, if there is a current, surface current density, then that would affect the parallel components of magnetic field. So that means the parallel components do have this discontinuity coming in if you have a surface current flowing through a surface. Okay. So this is how the normal and the tangential components look like below and above a surface. So these are the boundary conditions which come from the divergence and the curl of magnetic field. And just like you have electric dipole, you can also have magnetic dipole, right? But or in general, you can also have higher order terms. So you can have quadrupole, right? So the multipole expansion gives us the complete expansion of how the vector potential, or in case of electric field, how the scalar potential would look like. And based on what regime we are in, or what is our charge distribution, different terms from this multipole expansion would be the dominating term. Okay. So now what it tells us is that if you have some charge, some current, current carrying wire, you can always say that you can start with the Biot-Savart's law and you can try to find the magnetic field, but that would be a very tedious task. So what in general, what we try to do is we try to do first find the vector potential. Okay. And vector potential has a form like this. Okay. So now if you solve it, explicitly, you would get this individual terms. Each of these individual terms correspond to one particular dominating distribution. Okay. So first term is called the monopole term, second term is the dipole term, and similarly quadrupole, and so on. So because your for magnetic case there is no monopole, that means this term would always go to zero. Okay. So that would result in the fact that this first term is always zero. Now the second term is what is the dipole term. So if we can rearrange and write it, you would get finally an expression like this. So where m is your magnetic dipole moment and r is the distance from the dipole. So you can say that in this condition, this is how your vector potential will look like. And if you know the vector potential, you can use this relation to find the expression for magnetic field. And this is a very important expression which gives us the magnetic field for a magnetic dipole. Okay. And this is just in the vector form. And as you can see, because there is no monopole term, so the magnetic dipole moment is independent of the choice of origin. This is something one should remember. So now, because you have this magnetic dipole moment, based on what kind of medium you are in, there can be a net magnetization in presence of an effect. If suppose if you have an external magnetic field, based on what kind of medium you have, there can be different magnetization that can get generated. Okay, so if you have a diamagnetic material, that means in absence of field, there will be absolutely no magnetization. In presence of the field, what would happen is the individual dipoles would try to arrange in a direction opposite to the applied field. So because of which the magnetic field lines or the effective magnetic intensity inside a diamagnetic material will decrease from what you have outside. Okay. But in case of a paramagnetic material, when there is no field, there is no net magnetization. Once you apply a field, the moments get oriented in the direction of the field. So that results in intensification of magnetic field lines inside the material. Okay. And in case of ferromagnetic material, you always have a net magnetization. So initially also, if there's no external field, you will have a net magnetization. Once you apply a magnetic field, the moments will align in that direction. So that would again cause greater intensification of field intensity inside the ferromagnetic material. So based on different materials, the field intensities that one can experience in the material would change because of the magnetization property of your material. So now that you know the expression for magnetization, so you can understand, as we had for a polarized object, you will also have fields that would be generated for a magnetized object. You apply a field, the substance get magnetized. This magnetization itself results in a new field. Okay, so what would be that field? So if you want to find that field, so if this is your expression for A, you can have a volume integral over the region where you have your magnetized object to find the effective expression for your vector potential. And now, if you rearrange it further, just like the case for a polarized object in case of electrostatics, you will see that you can write it in terms of two terms. So the first term is a contribution coming from an effective volume current. Okay, this term here, which is given as curl of M. M is the magnetization. And the second term comes from a surface current, where surface current is given as M cross N cap. So that means now you can write A in, so this is the vector potential for a magnetized object. And you can write it in terms of these two contributions coming from two bound currents. One is a volume current, another is a surface current. Okay. So that means your Ampere's law will also get modified now because of the presence of this bound current. So if you include that, you would see that you would have an expression like this. Okay. So here H, or the auxiliary field, this term here only depends on what you apply externally, or the free current. Okay. While the B here has effects, or is the resultant field, which includes the effect of external causes as well as the bound currents. Okay. So if you now consider that the magnetization is proportional to the applied field, okay, then you can rearrange it further and you can write this expression where mu is now the permeability of the medium. So B is given as mu into H. Okay. So this was one question we had solved, and we had seen that. So if you say that you have a copper rod, some radius of some current I, so I here is the free current. So what you can do is you can use Ampere's law to find H first, and then use this relation to find B. Okay. Here again, based on the boundary conditions, you can just translate the boundary conditions of magnetic field to the boundary conditions for your auxiliary field as well. We also move to the concept of electromotive force. Okay, so where we had seen is that, so we saw that there's a, if you have a charge in presence of a magnetic field, it experiences some force, right? So that means now if you have, if you consider some battery, you connect, you make a circuit out of it, okay? So there in for what do I say? So if at a certain instance, if there is a net electric field that is generated, that would result in a net force. And if you have a source here, this source, if you say that the force coming from this driving source is Fs, and if you see that, say that the net field generated is E, then because it's electrostatics, if you consider, then you would say that E dot dl is zero. So that means effectively what you can see is that the net force that is generated can be actually coming from your battery or the driving source. And there you can define this term called the electromotive force, which is actually not a force. It's basically work done. So you do a line integral of that force your over the length of your circuit. So that is what is called the potential difference generates from that. So that is what is called the electromotive force. Basically, it's the work done by the battery in order to move a charge from one point of your, circuit to another, work done per unit charge. So from here, from the concept that, when you have moving charges in a magnetic field, it would experience a force. This initially, this concept of motional EMF came that, so if you have if you have a current carrying wire and if you move it in a magnetic region such that the net magnetic flux linked to that closed loop, if it changes, then that will result in a net EMF or net uh, potential, right? So this is what is called the motional EMF. So you have this closed loop, you move it such that the flux changes, and this flux change. So because you move it, you can consider that the charges are moving. So you can use the Lorentz, the magnetic force expression to find the net force and net work done, right? And one another way is as it is moving, the net flux linked to this region is changing. So you can find the net flux, net magnetic flux, and see how the flux is changing as you move it. And this rate of change of flux, as you can see, is equal, and like it's minus of the rate of change of flux is actually the EMF or the potential difference that generates. So that means it's this change in flux which is causing or which is resulting in this uh, effective potential. Okay. And there were this kind of questions where we saw that if you have a current carrying wire, if you have another loop like this, so here, because the magnetic field flux won't change if you move it along this line, if you move it along this line, there'll be no uh, EMF that would be generated. But if you move it in the perpendicular direction, the effective flux linked will change, and there you would have a net effective EMF that would be generated, right? So that shows that what lies at the heart of the generation of EMF is the change in magnetic flux. Okay, this was just a question that we had solved. So we can, if you know the magnetic field and how magnetic field is changing, how the flux is changing, you can find the EMF generated. So from there came the Faraday's law. Okay, so till now, when we had spoken about electrostatics, we had seen that the curl of the electric field goes to zero. And from there, we got a definition of our scalar potential. But that is electrostatics, where nothing is changing with time. But now what we saw is that if your magnetic flux changes, that results in a effective potential difference. So that means this potential difference would be related to some field. Okay. And this changing magnetic field can induce an electric field, which gave rise to the Faraday's law. So now if you can see that if you mathematically, if you write an expression for the EMF, okay, and here you have the flux. So in place of flux, if you write it as B dot dA, you would finally get to this expression. So this says that now if you have a time varying or a changing magnetic field, that would result in an effective electric field. And this electric field will have a non-zero curl, which will follow this relation. Okay. So that means these were the Maxwell's relations before, like these were the relations before Maxwell. But then what what we like this is what we had discussed so far. But now what came next was that this Ampere's law that you have here is not exactly complete. And why it is so is that we know divergence of curl of a quantity is always zero. And that is true, that holds for the Faraday's law. But that does not hold always for the Ampere's law. Why? Because for that to hold, your divergence of J should always go to zero, which is not necessarily true, which is true only in the case of steady currents, only in the case of magnetostatics. Otherwise, there is no reason to, have this condition that the divergence of J is zero. So that means this fundamental vector calculus theorem that we know, divergence of curl of some vector quantity is zero, is violated. So that means there's something wrong with this. Okay, and that led to a modification that was brought by Maxwell. So this final equation that you have here, this relation got modified by Maxwell to get to the final Maxwell's relation. And what was done is that we use the continuity equation, and there we know rho is again. So if you use this relation, you can write rho in terms of electric field. So now what we saw is that if you include this term in the divergence of J, you would see that there's a magnetic field, which is again related to changing electric field. So just like in case of Faraday's law, you had a changing magnetic field resulting in an electric field. Here you have a changing electric field resulting in a magnetic field. So this term here that you have is called the displacement current. Okay. So now this was how electrostatics and magnetostatics, which was initially dealt with separately, got connected. So a changing electric field results in magnetic field, a changing magnetic field results in electric field. So this is the final Maxwell's equations that we got. And here you can see how now the electric and the magnetic fields have got interconnected to each other. Okay. So next what happened is we try to work along this line. So we try to use these relations in cases of electromagnetic waves. So if you have some electromagnetic wave, okay, and there we, okay, so in free space, this is how it would look like if there is no external charge or no rho or no current. And then now what you can say is that you can use this vector calculus relations, curl of E or curl of B. Okay. And there you impose these conditions to get to this expression, which is nothing but the wave equation. And now if you compare it with a with the wave equation, you would see that 1 by mu naught epsilon naught is nothing but the speed of the wave, and that matches with the speed of light. So that means this again verified, or this established the fact that light is an electromagnetic wave. Okay. Now, this is for the case in vacuum. Okay. It will, if you have a different media, there the speed will again change based on the permittivity or permeability of that media. And this is how have you can use the Maxwell's relations to, if you know the electric field, you can use this relation to find the magnetic field. And with whenever you have a wave, you have an energy like electromagnetic wave propagation, there's an energy propagated through it, and this energy is quantified in terms of the Poynting vector, which is given by this relation, as you can see, E cross B by mu naught. So that means if you have some plane waves, this is how it will look like. So if you have some waves propagating in along Z, you will have an electric field, and the magnetic field will be perpendicular to it. Okay. And both electric field and magnetic field will be perpendicular to the direction of propagation, because these are transverse waves. In general terms, if you have a wave vector K, which denotes the direction of propagation, this is how your electric field and magnetic field will look like. And because it's transverse, n dot k will go to 0, where n is your polarization direction. Okay. And this is like in the general most term, this is how your k So with any general propagation vector k and polarization vector n, this is how your electric field and magnetic field will be related. And from there you can find an expression for Poynting vector, energy. So this is how the energy density, the uh, average of the Poynting vector, the momentum, the intensity, all these terms can be defined based on what is the electric field and the magnetic field. Now, if you have a different media, there again, everything will be the same, but now you have to consider the polarizability and the magnetization of the medium. So that means there your epsilon naught will be replaced by epsilon, mu naught will be replaced by mu. Okay. The speed of the wave will change because now you will have this term here. So that the ratio of the speeds is what is called the refractive index of the medium. And it's just a modification that will be followed in all the expressions. Okay. And similarly, now because you will have a different dielectric, so if you have different dielectric constants and if you have to define the boundary conditions, this is how the boundary conditions would look like. So there, this is the boundary condition that needs to be satisfied at the boundary where you have epsilon 1 as the dielectric constant on one side and epsilon 2 as the dielectric constant on the other side. So there, this is the relation that needs to be satisfied for the electric field and similarly for the magnetic field. Now, from here, again, this is just a, you know, detailed expression, which I'll not go into the details of it. But so whenever you talk about boundary conditions, if you get confused how to get to the boundary conditions, start with the Maxwell's relations. Okay. So when you will have line integrals there, if you take such a small segment and solve, you would see that the line integrals, if you write explicitly, will involve parallel components. So when you have this kind of terms like d dot dA, so there that means you are talking about the normal components of this vectors. Okay. So accordingly, from this relations, you can get to this all this boundary conditions, which will again which is actually what is being used when we talk about Fresnel coefficients and all that, right? These are the boundary conditions that we had used. So that's the next part. So we use this boundary conditions. You say that you have two different media. So there could be two different like electric fields would vary in the two regions. Electric field and magnetic fields would vary. The speed of the waves would vary in the two regions. But at the interface, they would follow the boundary conditions. And if you impose that, you can find a relation about how. So when you have a wave propagating from one region to another, some of it will be transmitted, some of it will be reflected back, and how much will depend on the boundary conditions, and you can impose that to find the ratios. So that gives us this ratios of how much of the light will be reflected or how much of the light will be transmitted and so on. Okay. Now, if you have a conducting surface, there you would have an extra term which would come because of the conductivity of the medium. So in that case, everything would remain the same. You would get similar expressions for, so this is how your wave equations would now get modified. But now if you solve for this equations, you would see that your wave number now will become complex quantity. So there, the real part will talk about the propagation, while the complex part will talk about attenuation. So that means if you have a conductor there, you will have attenuation of the wave, and how much will depend on this value here. So you have a skin depth where the amplitude reduces by 1 by E of the amplitude. So this is how the skin depth is defined. So you can see that electric and magnetic fields are exponentially decaying, are of exponentially decaying amplitude in case of a conducting media. Okay. And similarly, now if you include that, you can try to write an expression of, so this is phi. This is nothing but because your wave number is now a complex quantity, so it has an argument and it has an amplitude. Okay. And the argument results in a phase difference between your electric field and and a magnetic field. So the magnetic field here lags behind the electric field. And you can define the wave impedance as a ratio of the electric field to magnetic field. So in case of conductors, it would be a complex quantity. So this was about electrostatics, magnetostatics, and then we talked about electromotive force and how the electric field and magnetic fields get correlated in cases of time varying situations. And then we move towards, lumped and distributed circuits. So there what we saw is that now we understand how waves propagate and the basis of Maxwell's relations, and that's okay. But now if you have some circuit or some, connections, there's a some connecting circuits, not but now based on what is your frequency of your signal and what are the dimensions of your connecting leads or connecting wires, we saw that the connecting leads by itself can also affect the signal that is being transmitted. If it is not affected, then it's in the lumped region, while if it is affected, then it's in the distributed region, right? And that depends on what is the dimension of your wave, what is the frequency or wavelength of your signal. Okay, all of that. Now, if it is in the distributed regime, there you have to consider, or you can consider the effect of the transmission line in terms of this four parameters: G, R, L, and C. Okay, so this is how you can. So if this is a transmission line, you can break it into small unit cells, which involve this four parameters, and how small depends on the fact that you have to make it much smaller than the shortest wavelength that is being transmitted. Okay, so now if you look at individual sections, you can use it to find the effective. So in each of these individual sections, they are individually a lumped circuit. So here you can apply your Kirchhoff's laws to find how the potentials of the currents are, and then look at the net effect of the entire transmission line. So if you apply KVL and KCL to a unit cell, this is how your potential and you know all the different terms or different distributed parameters are related to each other, or the current. And from here you can get to an expression like this. Okay, in the case where there is no loss, so you consider R and G to be zero. So there you see that now you can write the potential as a summation of a forward and a backward moving wave. Okay, and this is the wave velocity. So it's a wave equation that you get. Okay, so that means in this section, if you have to write the potential is like a wave. It is propagating through this like a wave, given by this relation here. So that means if you start with some, so at one end at the source, if you have some potential, as it propagates, it can it can acquire different phases as it propagates, right? How much, that depends on what are the distributed parameters. Okay, so if you start with some potential, use these relations which come from the Kirchhoff's law. Okay, you would get an expression like this. This is a forward moving wave and a backward moving wave. Here alpha is like the attenuation coefficient, while beta is like the phase coefficient. So the beta tells you what is the phase that gets added to your signal, while alpha talks about what is the attenuation that the potential goes through as it transmits from one side to another. Okay, and in the ratio of the potential to the current is is what defines the characteristic impedance of your transmission line. Okay, so for different cases, depending on different values of R, G, L, and C, or the different conditions that they satisfy, you would get different expressions for your characteristic impedance, and that would define what kind of wave you have, right? So if this condition is satisfied, it's a distortionless line. While if it's a lossless line, then R and G would go to zero. So based on what are the distributed parameters, your transmission lines would be defined accordingly. And the phase velocity will be given by this relation here. So here omega by beta will be the phase velocity. Okay, and for the lossless case, the velocity, right? Which is given as 1 by LC, and it is same as what we get from this relation. And if it is not lossless, if there is a net alpha, then the potential amplitude will gradually decrease, which is given by this relation here. So how much distance will it have to travel for a certain decrease depends on alpha. And this is how you can define it in terms of dB. Now, if you have a net, if you have a termination, so now if you have a transmission line and at the end, if there is a net load, based on what is the value of the load and what is the value at the source, depending on this impedance and how the impedances differ from each other, you can have, uh, the net effective signal that you see at the incidence would vary. Why? Because this was how we did it. So in general, the potential on a transmission line looks like this, and the current looks like this. So you can now apply boundary conditions at the load end and at the source end. So at the load end, you can say that your V by I should match with your load impedance. And if you do that, that would give you an effective expression for reflection, if there is any reflection. So if your impedance of your transmission line matches with your load, there would be no reflection. If it does not match, there would be an effective reflection, and that reflection coefficient is given by this relation here, which involves both the load impedance as well as the characteristic impedance of your transmission line. And now if you apply the boundary condition at the source, there again, you would see if you solve it like just the ratio of the potential to current, and you would see that now the incidence, the load impedance that you see at the source, again depends on the length of your transmission line, the characteristic impedance of your transmission line, and the load impedance. Okay. So this is how these are related. So based on how long your transmission lines are, so this was the relations that we saw, that based on the distributed parameters and the length, okay, you can have different, you can see how the load at the incidence is related to the characteristic impedance and the lengths, right? So this L here is the length of your transmission line. So we had solved questions which involved all these different conditions. Now, next thing that we spoke about was about waveguides. So in one side, we have transmission lines where there are two conductors involved, which talks about TEM modes, where waves get propagated with a few gigahertz of signals. But then you can have waveguides where there is only one conductor that is involved. And we saw that their TEM modes were not satisfied, mainly because, you know, we saw that the EX, EY, BX, BY components were related to the propagation direction component, like EZ and BZ components. And if you now set EZ, BZ to 0, the entire field goes up, right? So there we saw that you can have different modes, TE and TM modes. And based on what your dimensions of your waveguides are, you can have different cutoff frequencies. So different frequencies can propagate through waveguides based on their dimensions, and it can last till terahertz regions as well. So I would not go into the details of it, but what we saw basically is that this is how you can see that the EXEY, BXBY components are related to the EZ-BZ components, which is the component in the direction of propagation. So that means here you cannot have EZ-BZ going to 0. So you cannot have TEM waves. Now, from here, what you can say is that now if you know EZ and BZ, you know all these four terms. So from here, you can write coupled equations of, like, use the Maxwell's relations to find uncoupled equations of EZ and BZ. And these are nothing but, very simple differential equations. So you can solve it further to find expressions of EZ and BZ. And based on whether you have TE mode or TM mode, you can set EZ or BZ to 0 and accordingly find the different components. So if you consider TE mode, then your EZ will go to 0. And then what you have to find is BZ. And there again, you use the separation of variables, okay? And use this relations of the wave vectors. Here, when you apply the boundary conditions, so you have to apply the boundary conditions based on the dimensions of your waveguide, right? So based on the dimensions, you would get the possible values of your kx, ky components. And that will set the expression for your uh, bz component for TE modes. For TM modes, again, you will have some values of kx, ky, and that would set the expression for Ez in case of TM waves. And then once you know kx and ky, you can try to write an expression for k. Okay, this is in the propagating direction. Okay, and this is now telling you that below a certain frequency, waves do not propagate, and that sets the cutoff frequency. So for a particular mode, which defines the kind of wave that is being propagated. So for a particular mode, based on the dimensions of your waveguide, you would have a particular cutoff frequency, below which things don't propagate. Okay. Okay. So another way of looking at it was in terms of reflections. We did see that when we talk about, even later when we spoke about the other kinds of waveguides, there this reflection at the different interfaces did play a role. The take home message is this. So when you have waveguides based on the dimensions, you have different cutoffs, and this acts as a high pass filter. Similarly, you can have for a TM mode, and you have to remember that the cutoff frequency expression in the general expression for TE and TM modes are the same, but the smallest cutoff for TE mode corresponds to the fact where you can put one of M and N to go to 0, while in case of TM modes, both M and N starts from 1. So your smallest mode corresponds, lowest TM mode corresponds to M equal to 1, N equal to 1. Okay. And then we spoke about other kinds of waveguides where we had this plane mirror waveguides. And there we saw that for the wave to propagate, there is a self-consistency condition, which means the wave that you have here should be same as the wave that you have after two successive reflections. And that gave rise to this condition that you have here. So that sets the possible values of theta m that one can have based on this dimension that you have, the distance that you have between the two mirrors. Okay. And from here, you could look at the possible values of ky, and you can see that the transverse wave component now has this possible discrete values. Okay. And that sets the possible modes that one can have. Okay. And here, as you can see, we saw that if the value of d, or the displacement, the distance between these two mirrors, if it is such that 2d by lambda is less than 1, then their m goes to 0, and it basically supports no modes. So there is a cutoff wavelength which is defined as 2 into d. So below this, again, there would be no modes that would be supported by your waveguide. Okay. And then we talked about planar dielectric waveguides, where you have, so basically now you have sandwiched up dielectric media of some dielectric constant N1 between two other dielectric media, and N of a different different refractive index, and N2, and this N2 is less than N1. Okay. And this is necessary for the waves to undergo total internal reflection, so that there is less attenuation and the wave propagates. Okay. And the difference that all the other things are the same, but the difference that this thing is there from the planar mirror waveguide is that here, whenever there is a reflection, there is a pi phase change, while here the phase change again depends on the angle in which it is incident. And that comes from the fact that now if you have these two different media. So based on your reflection coefficients can also become complex. So that can add an additional phase. Okay. And if you have a media where N1 is greater than N2, there is a possibility of total internal reflection based on which incident angle your wave is falling. And based on that, this is the relation that the additional phase that gets added. This phi is the additional phase. So this is the condition that it satisfies. Okay. So there you can see beyond a certain value, your all of it gets reflected. So there you have total internal reflection beyond a certain value of angle incidence. And that sets the limit of the number of modes that you can have, because now you have this phi r here, and this phi r again follows this condition, and this is a transcendental equation. So if you have to solve this, you have to solve it, see which are the points where they intersect, and that sets the limit to the number of TE modes that one can have, or the number of modes that one can have in general. Okay. And this is the relation which sets the number of modes. Okay. And as you can see, it depends on how the refractive indices of the two media vary. Okay. And if you have the case where lambda by 2d is greater than sine theta c, that means there can be only one mode. So that is that in those conditions, the waveguide is called a single mode waveguide. Right. And this is how so this is just writing it in terms of frequency. Okay. Cutoff frequency. And this was at the last class what we had discussed. So we had spoke about radiating sources, we had spoken about antenna, and there again, this is nothing but writing the same Maxwell's relations, but now in terms of potentials, scalar and vector potentials. So there we saw that this is how you write magnetic field in terms of vector potential. This is how you write electric field in terms of scalar and vector potentials. And if you include that in your expressions of Maxwell's relations, you would get expressions like this. One can simplify this expression by proper choice of A, okay? And you have the liberty to choose A such that your B does not change, okay? Both A and B, as long as E and B does not change. And that sets the different gauge transformations that one can have, okay? And these are this is how, so if you add this term, uh, any function of this form to A and V, then the effective magnetic field or the electric field won't change. So based on this, you can have different gauges. One is a Coulomb gauge, okay, where you put divergence of A going to 0, and this gives you a very simplified form of potential, which is same as the Poisson equation that we had initially seen for electrostatics. But in this case, the expression for the vector potential still remains complicated. If you want to simplify this further, there you have to consider the Lorentz case, which is given by this relation here. Here it puts A and V into equal footing. Okay, and this operator here is termed as the D'Lambertian operator. Okay, and this is how you can see that, now if you can use this relation to find V and A, you can try to find E and B from there. So interestingly, if you have a radiating source, and then if you want to see what is the field at a different instant from that source, it would take some time, some finite time for the electromagnetic wave to propagate, okay, because it propagates with a finite speed, like a speed of light in free space. So that gives the concept of retarded time, which says that if you look at a potential at a certain point, but now if you have time varying effects coming in, if you have a radiating source, which is where the electric and the magnetic fields are changing with time. So there, the effect of potential at a particular point, or the effect of the vector or the scalar potential at a particular point, will be affected by the volume or the current density at some time prior to it. And how much prior will be dependent on how far you are from the source. Okay, and this is how it looks like. Based on that, we tried to find an expression for the Hertzian dipole antenna. So there we found the expression for A, and then wrote it in the cylindrical coordinate system and used it to find the expression for field. We saw that, so once you find field, you can also use it to find E. So we saw that based on how far you are from the radiating source, different terms would dominate, and that would set the different regimes. So if you are in the far regime, you would see that their 1 by r terms would dominate. If you are in the near field regime, their 1 by r cube terms would dominate, while in an intermediate regime, your 1 by r squared will dominate. And what is the intermediate regime defined by? So there beta into r is equal to 1, or it's considered to be 1, and beta is given as 2 pi by lambda. Okay, so based on the wavelength of your light, or wavelength of your signal, and the dimension, or like how far you are from your radiating source, you can choose which region you are in. Okay. And because you know the electric field now, you know the magnetic field now, so you can use it to find the power. You can try to find the expression for the Poynting vector and try to find the effective power that is being radiated from the source. And this is the expression for the total power radiated. There is no radial dependence, as you can see. Okay, it depends on, so if you have some dipole antenna, the current through the antenna, the dimension of the antenna, how far, what is the wavelength, so what is the dimension, and then what is the wavelength of your signal, right? So, and the medium, because you have eta naught here. Now if you have a different media, so if it is not free space, then this term will also get modified. We did solve some questions where we saw that if you put the antenna in water, the power or the required current changed, right? And that is because the medium properties changed. So this is the expression for the total power that is being radiated, and from there you can define, so you can just write it in this form where you can define a radiation resistance. Okay, and based on what the dimensions of your antenna are, or what is the, with respect to, so dimension of the antenna with respect to the wavelength that is being propagated, you can have different expressions for radiation resistance, and that can give you the expression for the total power that is radiated. Right, so that was about what we had discussed all throughout the course. um, I hope the entire course and also today's summary would be of some help to all of you, and thank you your mm, for listening. Thank you. Any questions or any comments, you can tell me. Okay. Okay, guys, so that it then. All the best for your exams and all your future endeavors. Thank you. Yeah, thank you. That was the aim of the revision class. You can, so I did not have any numericals here because I just went through the concepts. Uh, you can just go through the individual sessions for the questions or numericals. And yeah, thank you. Okay, bye bye.